The next thing we're looking at is weight versus mass. So for the most part, we understand what weight versus mass is. We know that mass is a scalar quantity. And we know that weight is a vector quantity. Now, mass is a measurement of how much of matter is in an object. And when we look at weight, we're looking at how hard gravity is pulling on the object. But neither of these things is foreign to you, so you should know that. Your mass is the same everywhere you are, on Earth, on the moon, floating in space, because the amount of stuff that you are made of doesn't change. Yes, and when you growing up, your mass does change, but if your mass is 65 on Earth and then you take a trip to live on Mars, you're still going to be 65 kilograms. Your weight is dependent on how strong the gravitational force is acting on you in that moment. So you'd weigh less on the moon than on Earth, and in space you'd weigh almost nothing. So mass is measured in kilograms, we know that, and weight is measured in newtons. So when you stand on a scale and you're trying to measure how much of you there is, people who are trying to reduce their mass hope to see the reading on the scale to get smaller. And they talk about losing weight. Their weight will decrease, but because their mass is decreasing. So I know that the relationship between weight and mass is directly proportional. So weight is directly proportional to mass. That's my relationship there. And essentially what I'm looking at is the fact that my weight is also my force of gravity. So I can say that weight is also force of gravity. So Fg is equal to mg, which we know now, where Fg is your weight or your force of gravity. M over here is your mass in kilograms, and G over here is your gravitational acceleration. And on Earth, that value is 9.8 meters per second squared. Alright, so that's the basis of what's about to happen. Next, we're looking at the lift problem. So I'm going to bring in the lift problem here before we get into relationships for your Newton's gravitational force, because it comes in handy when we're working with the next little bit. Alright, so what we're looking at now is Newton's laws and G. That's your little heading there. So I've got here a lift with a mass. A lift with a mass of 250 kilograms is initially at rest on the ground floor of a tall building. Passengers with an unknown total mass, m, climb into the lift. The lift accelerates upwards at 1.6 meters per second squared. The cable supporting the lift exerts a constant upward force of 7,700 newtons. And we're going to need all of this information to sort our lives out, but we'll get to that. The first question says, draw a labeled force diagram indicating all the forces acting on the lift while it accelerates upwards. And the second question says, what is the maximum mass of the passengers the lift can carry in order to achieve a constant upward acceleration of 1.6 meters per second squared. So we want mass here, and here we want a force diagram. So let's have a look at our force diagram. Let's have a look at this force diagram. Alright, so I've got myself a little force diagram. Remember, free body diagrams are different from force diagrams. This force diagram here is representing my object. And the first thing I need to do is I'm going to choose a positive direction. So I'm going to say if the lift moves upwards, I'm going to consider that a positive motion. All right, so the first thing that's happening here is I want to know what kinds of forces I have on this object. The first force I have, and I can draw it in here, is I know that I have a force here of gravity. So I have my Fg or I have my Mg or whatever the case is. You would use a ruler, right? At the exact same time, this is the Fg of my passengers. Oops. At the exact same time, I have another force also going down this way, and that is my Fg, of the lift itself. So I can say that that one is my downward force of the earth on the lift, and the other one would be, just make a note here, the downward force of the passengers weight. Right, that's two. Right, they kind of in sync with each other. The third force I have is because this lift is being pulled upwards by a rope, I've got a force of my cable, or I can call it a force of tension. And this here is the upward force of the cable of the lift. And I know that the force of that tension is 7,700 newtons. All right, so this is what your free body diagram would look like for question 1. Right. Then let's have a look at question 2. Question 2 says, what is the maximum mass of the passengers the lift can carry in order to achieve a constant upward acceleration of 1.6 meters per second squared? All right. The first thing we need to know or understand here for question 2 is gravitational force. All right. With the gravitational force, we know that the gravitational acceleration of an object that's on Earth, due to the Earth, I know that the G value that we're going to be using here is 9.8 meters per second squared towards the center of the Earth. So I know it's going downwards. So we know that the force due to gravity on the lift or the passengers is Fg is equal to mg, right? So this is the first little equation we have. Now, we learned 3 steps for lifts and motions of lifts. So let's have a look at that. Right, now in this whole thing, I've got different scenarios. So the scenario that I have is that I've got this upward acceleration that's happening. So now my problem is I need to sort out all of my information. So let's just have a look here. I know that F net is equal to MA, right? So that's the first thing. I also know that I have upwards and downward forces. So let's have a look at that. In my upward direction, I've got that. So in terms of an upward force, I've got 7,700 newtons going this way. But my downward force, I have 2 things. I have Fg lift and Fg passengers. So I've got mg for the lift and I've got mg for the passengers. Right. Now for the lift, I know the mass value is equal to 250 kilograms, and I know the g value is equal to 9.8 meters per second squared. For the passengers, I don't know the mass, but I know that the g is equal to 9.8 meters per second squared. Right. So between the two, I know the g has to be the same. Now both of these, if I add them together, right, if I add up mg lift plus mg of the passengers, that's going to give me the weight, right? So now I'm left with 250, right, times 9.8 plus mass of the passengers times 9.8. So what I can do is between the two, I can take out the 9.8, and what I'm left with now for the downward force, I've got 9.8, whoops, which I took out as a common, 250 plus mass of the passengers. So that's my downward force. So now I've got, let's have a look here, an upward force there and a downward force here. So now I need to put all of that information into my formula. Now I know that F net, we use that silly thing, F net is equals to the forward minus the backward. So now we've got, instead of forward and backwards, we've got whatever's up minus whatever is down. So now I need to put all of that into this formula and get an equation sorted out. So let's have a look at what I have. Right. I've got F net is equal, oops, let's write it properly, right? F net is equal to MA. My F net, my upward force, which I'm considering as positive, is 7,700 minus 9.8 times 250 plus mass of my passengers, which is equal to my mass, which is going to still be 250 plus mass of my passengers, and my acceleration of this whole thing was 1.6. So let's sort all of that information out. Okay, let's have a look here. I've got 7,700 minus 9.8 times 250 is 2,450, and then again minus 9.8 MP is equal to 250 times 1.6, which is 400, plus 1.6 MP. Alright, so I'm going to take 7,700 minus 2,450 minus 400 is equal to 1.6 MP plus 9.8 MP. Alright, if I pop everything into my calculator, I'm going to get 4,850 minus, is equal to 11.4 MP. Divide both sides by 11.4, and then my mass of my passengers is equal to 425.438, so 0.44 kilograms. And that is your final answer, and you've got to answer the question. The question says, what is the maximum mass M of passengers the lift can carry in order to achieve that amount of 1.6, an acceleration of 1.6, and then you can say, therefore, the total mass of passengers is 425.44 kilograms. And that's how you do a lift problem dealing with FG, MG, or whatever the case is. Alright, so the next thing we're looking at is relationships. So what you would notice that I know that you guys come across multiple sources, multiple textbooks, and you might find different formulas, but it's exactly the same thing. So the thing that is different between these formulas, and you'll see it here, I'm just going to highlight it for you, is sometimes you get d squared and r squared. Essentially, for d squared or r squared, it is still the distance and it is still measured in meters with a little m. Right, that doesn't change. For the intensive purposes, for this little thing that we're going to do now, is we're going to look at the relationship between force, mass, and distance. So you need both formulas so that what comes next makes a little bit of sense. Alright, so when I'm looking at these formulas, what I want us to imagine, right, is that when we look at proportional relationships or inversely proportional relationships, this is how we work that out. So let's just have a look here. But over here. Alright, so essentially what's happening here is this is force over 1, force over 1. So two relationships are kind of forming here. The first relationship that's forming, let's just get that out of the way, is the relationship between force and mass. So let's look at the first one. Force versus mass, right? And I can see that the force is at the top of the fraction. Have a look. And the product of the mass is at the top of the fraction. So already now I can see there's a directly proportional relationship. So I can say that the force is directly proportional to mass 1 multiplied by mass 2. All right. So here I've got a directly proportional relationship. But it's not just directly proportional. We must, if I say it in words, the gravitational force is directly proportional to the product, meaning multiplication, of the masses. Right. So that's your relationship, force and mass. Your other relationship is force and distance, and see the shape that it forms. One's at the top, one's at the bottom. So the second relationship you have, so let's get that out of the way. The second relationship you have is between force versus distance. So what we can say here is, because the relationship is inversely proportional, how we write that down mathematically is we say force is directly proportional to the inverse of the radius squared. So the gravitational force is directly proportional to the inverse of the distance squared. I can even write that as force is directly proportional to distance squared. right? It doesn't matter. So if I had to look at this, and let's say I say double the mass, how will that affect the force? One must go up, one must go down. I will end up double the force, right? If I look at distance, if I double the distance, because it's a fraction and then it is squared, what my result is going to be is it's going to be quarter the force. I'm going to show you guys how to make that work. But this is the types of relationships that you must understand between force versus mass and force versus distance for the gravitational law. All right, let's have a look here. So what we're looking at is, what I can draw, just move this again out of the way. So I can draw a little bit of a triangle. And my triangle for this formula is going to look like this. GM1, M2 is the FG and the R squared. Alright, so if I want to find either one of these things, just cover up the others and I can manipulate my formula. So that's important as well. Alright, let's have a look at the two things. Right, over here, I've got this little setup here. Okay, just going to go through mass first and then we'll go through the other one. Right, so the first thing I'm looking at is, I'm looking at mass. Now what you will notice about each of these mass diagrams is we're going to change the mass, and we're going to see how it affects force. And in this one, the distance, and you'll notice about the distance, remains constant. Okay, so we're looking at mass and we're looking at how it affects force. All right, so let's look at the first one. I suggest you draw these so that it's easier to understand, because this is one of the main types of questions for gravitational acceleration of gravitational laws. It's in your interest to look at it. So if I have here the first one, right? I've got one mass, and one force. Right? So 1, 1, 1. So all we do is, when we're going to do these types of calculations or these types of questions, they're going to ask you to increase one of the masses or decrease the masses, or whatever the case is. It's fine. We have a foolproof way. So what we're going to do is, for the masses, we're going to take 1 times 1. So mass times mass. And 1 times 1 is equal to 1 force. All right. In the second question, if I increase one of my masses to 2, so I double the one mass, all I'm going to do is say mass 1 times the second mass, which is 2, and that's going to give me twice the force. So if I double one mass, all right, I'm increasing the mass, then it's going to be double the force. So look at the second one. The third one, sorry. I've got 2 masses, so I've doubled here and I've doubled there. So now I've got mass 2, and the second mass is 2 times 2, and that's going to give me 4 times the force. So if I double both masses, that's double one mass. If I double both masses, right, it's going to give me 4 times the force, because there must be multiplied. I'm showing you how you substitute into the formula. All right. The second thing we're looking, the fourth thing we're looking at is here they tripled one mass. So you've got a mass 1 times the second mass, which is 3, and you're going to end up with 3 times the force. So when you do these kinds of calculations, all you're doing is whatever they tell you to increase or decrease, you do that to the formula. And that is how your mass is going to affect your force. Because your mass is a product of 2 masses. So you have to do a product sum. And that product sum is going to give you your force, your resultant force there. All right? Let's have a look here at the next one. All right. The second one we have here is we're looking at distance. And what you will notice is that the masses remain constant. But here we're looking at distance and its effect on force. So also draw these out, so it helps you out. So here what we're looking at is we're looking at mass 1 times mass 2 all over r squared. Right, so let's have a look at how this works. So for the first one, I have a single mass, 1 times 1. My distance is also 1 squared. So now I've got 1 times 1, which is 1 over 1, which means I'm left with 1 force. So if the distance remains constant and you have a single mass, 2 single masses, and 1 distance, then you're going to get 1 Fg. Right. If you look at the second one, they're saying the masses stay the same, but the distance doubles. So here we're going to double the distance, but the masses stay the same. So I've got 1 times 1 all over 2 squared. So I've got 1 over 2 squared is 4. So therefore I've got a quarter of a force. So if I double the distance, I'm going to cut the force in 4 pieces. I'm only going to get a quarter. So that's showing me that the further I go, the less the force. But we're going to ask you by what factor. Or we're going to tell you the factor and you're going to have to do the calculation. Let's look at the next one, number 3 here. You've got 2 single masses, but you've got half the distance. Right? So what we do is we say, 1 times 1 all over a half squared. Now that gives me 1 over 4. So we want to take 1 and divide it by a quarter, and you're going to get 4 times the force. So all I'm doing is I'm putting all of this information to my calculator. My calculator is sorting it out for me. Right. Then I have a different one here. Have a look at this last one. The last one, what they've done is they double the mass and they double the distance. So let's have a look at that. So now I've got 2 times 2 all over 2 squared. 2 times 2 is 4 and 2 squared is 4, and 4 over 4 is equal to 1 force. So if I double the mass and double the distance, I'm going to keep getting the same force. So this last one is the exact same as the first one. So now you're learning relationships. If I double the distance, double the mass, then I'm going to get double the force. But I'm doubling the distance also, which means I'm taking it far. So it's getting bigger, but further at the exact same time. So it's going this way and it's going that way at the same time. So what you're getting here is just a basic force. So you need to understand two things from here. If I have more mass, I'm going to get a bigger force of attraction. Right? If I have more distance, I'm going to get a less force of attraction. Alright, so another thing that you've got to also remember, and I've spoken about this in previous videos leading up to this, is that if I had two circles or two planetary bodies, what I'm looking at is, I'm looking at that distance. So the distance that we deal with is from the center to the center. Therefore, we know it's your radius times 2, and that gives me your diameter. Right. So that is your whole idea for relationships, and what we're going to look at next are the different ways in which they can ask you these questions, and they usually come in multiple choice or they come within your question, but I want to show you different types so you can get a good idea of how you answer these types of questions. If I had speed is equal to distance over time, right, what that translates to is speed over 1, which is equal to distance over time, because any whole number by itself is a fraction over 1. Now, if a relationship forms by two variables at the top, that relationship, we say, is directly proportional. So therefore, speed is directly proportional to distance. If one variable is at the top of the fraction and the other variables at the bottom of a fraction, it forms this kind of shape, and we call that an inverse relationship. Right? So therefore, speed inversely proportional or directly proportional to 1 over time. Right? That is how, so we say it is inversely proportional. Right? We know that directly proportional means is if the one goes up, the other one also goes up. Here, if the speed goes up, then the time becomes shorter. Those are the kind of relationships we're talking about. So we're looking at this kind of setup. And what we're looking at here is we're looking at something called comparative problems. Now, comparative problems involve calculation of something in terms of something else that we know. For example, just do a little example for you here. If your weight on Earth is 490 newtons, let's say, for example, right? And then they tell you the gravitational acceleration on Venus is 0.903 that of the gravitational acceleration on Earth, what is your weight on Venus? All right, so all we do now is we take your 490 and you multiply it by 0.903, and then you get 442.50 newtons on Venus. So if I look at this information, that's my weight. Your gravitational acceleration is that amount versus Earth. That's how much I weigh on Earth. So multiplying it by that little factor is going to give me my weight on Venus. So that's the basic kind of questions that we're going to look at. So let's have a look quickly at your methods. The first thing is write out the equations and calculate all quantities for the given situation. Write out the relationships between the variables from the first and second case. Write out your second case. Substitute all the first case variables into the second case. And then write the second case in terms of the first case. So it all sounds like a loop of things, but we're going to have a look at some examples and I'll show you how we get through these. Right, let's have a look at the first one. A man has a mass of 70 kilograms. The planet Zygon has the same size as Earth, but twice the mass of Earth. Right? What would the man weigh on Zygon if the gravitational acceleration on Earth is 9.8 meters per second squared? Right, so all you're looking now is at a relationship kind of problem. So what we've got is the mass of the man, right, at 70 kilograms. We've got the mass of Zygon. So let's say we call that mz in terms of the mass of Earth. So we've got this mass of Zygon, and what they're saying is the mass of Zygon is equal to 2 times the mass of Earth. Okay. We've then got the radius of Zygon, right? So the radius of Zygon. And they're telling us that the radius of Zygon is equal to the radius of Earth. Alright, so the next thing that we need to do here is we need to determine how to approach the problem. So in the end, we want to determine the man's weight. We want man's weight on Zygon, right? That's the goal, right? So we can do this by looking at information that we do know. So I know that Fg is equal to mg, which is equal to, so this is whatever is happening on Earth, right? Which is going to give me g, mass of the Earth, times the mass of any other planet, all over r squared. But I know the man's mass is 70, and I know that the gravitational acceleration on Earth is 9.8. So the man's Fg is equal to 70 times 9.8, which is going to give me 686 newtons. So that is on Earth. Now we need to find out this value, its weight, right? The weight on this planet here. So let's have a look here. When you do these types of questions, you take the formula that you've been given and you change what is required only. Everything else remains as the value 1. Everything else changes. So if they say double this mass or double that mass. So the next step we're going to do here is we're going to look at the situation on Zygon in terms of Earth. Right. Okay. So we've done Earth. That's great. Now we move on to Zygon. Right. With Zygon, we know that we want the weight. So we're looking for Fg on Zygon. Fg is equal to G, the mass of Zygon, times the mass of any other planet, all over r squared. But now they're telling us what we know about Zygon, okay, is that if I want the force of gravity on Zygon, I've got to take G, 2 times the mass, the mass of Zygon, multiply 2 times the mass of Earth, all over r squared. Now I need to sort out whatever information I don't have. So I don't have that, and that's it. So everywhere else gets a 1, right? So I'm going to put it in and I'm going to say, for G, I'm putting a 1 because they didn't tell me that changes, multiplied by the mass of Zygon, which is 1, multiplied by 2, that's the mass of Earth, all of that over the radius, which they said was the same, 1 squared. So now I've got the force of gravity on Zygon as 2. Right? Now, when I look at my formula, just have a look here. Can you see that this formula here and this formula here are exactly the same, where this little m here is the mass of Zygon, and they're telling us we have twice the mass. So technically for Earth, we already have the force on Earth. So we've got 2, the force of Earth, on Earth. So in order to get his force of gravity on Zygon, we're going to say 2 times whatever the force was on Earth, and we found that the force on Earth was that value there, which is 2 times 686 newtons, and that gives me the force of gravity as 1372 newtons downwards on planet Zygon. Right? So therefore the man weighs 1372 newtons on Zygon. I know it's complicated, but we're going to do a few problems like this, and then you can see how you would solve something like this. A man has a mass of 70 kilograms on the planet Beeble. How much will he weigh if Beeble has a mass half that of Earth and a radius that's 1/4 of Earth? And we know the gravitational acceleration. So let's see how we're going to change this. Again, here we have the mass of the man at 70 kilograms. Great. Now we have the mass of planet Beeble in relation to Earth. They're saying that the mass of Beeble is equal to half the mass of the Earth. Okay. They also tell us the radius of Beagle. And they tell us that the radius of Beagle now, in terms of Earth, is 1/4 the radius on Earth. So that's what we know so far. So the first thing we need to know is, because we're looking at weight, like in the previous example, we need to find out what is this guy's situation on Earth. So I know that Fg is equal to mg, and mg is equal to g, mass of the Earth, all over the radius squared on Earth. Okay. So I know that this person is 70 times 9.8 and is 686 newtons. 686 newtons. That's his situation on Earth. We now need to have a look on what's happening on Beagle. Alright, so if I had the force on Beagle, I would have the mg of Beagle, which would give me g is equal to m on Beagle over r squared on Beagle. Right. But now we need to look at Beagle in terms of what's happening on Earth. So I know that in order to get this going, I've got g, I've got half of the mass of Earth divided by 1/4 of the radius squared on Earth. Alright, so now, what's a half divided by, sorry, just fix that. It's 1/4, sorry, 1/4 a radius squared on Earth divided by 1/4 squared. So now I've got 1 multiplied by 1/2 all over 1/4 squared. And that's going to give me my mg of Beagle equal to 8. So if I look at this little bit over here, I work that out at 686. So I've got 8 times the force on Earth, and my force on Earth was 686, and 8 times 686 is 5488 newtons, and therefore the man weighs 5,488 newtons on planet Beagle. Don't forget here it's downwards, because that's weight. Alright, so we're going to do more of these, but this is the general idea of how you do these calculations. And let's have a look at something like this. 2 objects have a mass 2x and 3x respectively, where x is the unknown quantity. Exert a force F on each other when they are a certain distance apart. What will be the force between the 2 objects situated the same distance apart but having a mass of 5 and 6x respectively? Right. The first thing you need to do here is you need to look at your 2 situations. You have F1. Let's do it here at the bottom. You have F1 here, which is equal to g 2x 3x all over r squared, and at the same time you have F2, which is equal to g 5x times 6x all over r squared. And now they want what will be the force between the 2 objects the same distance apart. So they want to know whether these two situations, what would be their forces. So let's have a look at what that's going to look like. So we can say now, I can transform these two things. We want to know if they're the same distance apart. We want to know what's happening with their forces, right? So the first thing I'm going to do is make the radius your formula. So because they're the same distance, I can say that r squared here is equal to g 2x times 3x all divided by f1. And on the other side, I can say r squared is equal to g 5x times 6x all over f2. Right, that's my situation. Remember what I said? If we don't know the values or they haven't spoken to us about anything about the values, then we put a 1 in. So G usually always gets a 1. So the first thing you need to know here is that the distances are equal. So I know that, let's do that, r squared 1 is equal to r squared 2. So I can equate these two formulas. So let's equate them and have a look. So now what I have is my G becomes a 1, and I've still got 2x times 3x all over f1, which is equal to, my G still becomes a 1, substituting that in, and we're looking for force, so we're going to just leave that symbol there, which is still equal to 5x times 6x, and all of that is over f2. Right, now that you have that all equated to each other, let's start doing some basic maths. So the first thing is 2x times 3x is going to give me 6x squared all over f1, which is equal to 1 times 5x times 6x is equal to 30. Oops. Whoa. 30x squared all over f2. Now I need to simplify this. And so we do basic math, cross multiply. I'm going to end up at 6x squared f2 is equal to 30x squared f1. Right, I can simplify both sides. The best way is to divide both sides by 6x squared divided by 6x squared. And now I've got f2 is equal to 5f1. All right, so there's my answer. So I need to go into my multiple choice and I need to have a look at which is the correct one. So it can't be 1, 2, 3, and my answer is number 4. So the answer is 5f. And that's how you get to your answer. So you've got to sit and go through these. Sometimes it's in multiple choice, other times it's just straight up there. Have a look at the next one. As the distance of an object above the surface of the earth is increased, the weight of the object would. So now you have your planet, right? And you're here, then you're here, then you're here. So if I had to check your weight at each point, right? Your mass is constant. But as you go further and further away from the center of the earth, then you should know that, number one, it can't remain the same because That's if we're talking about mass, so that can be eliminated. You are going further and further away. So the closer you are to the Earth's surface here, closer you are to the surface, the more you're affected by gravity. Now the fact that you're going away from it means it can only be decrease. Now if they had to ask you why, you could say that the distance is inversely proportional to the weight, or rather the force of gravity. And so, as the distance increases, the weight decreases. And remember what we said. If you're in outer space, you weigh practically nothing. But if you're sitting on this Earth's surface, you weigh something. So think about it like that. And that's how you make a decision. Right, a satellite circles around the Earth at a height where the gravitational force is a factor 4 less than at the surface of the Earth. If the Earth's radius is r, then the height of the satellite above the surface is... Okay, so let's have a look here. The first thing I want to do is I want to draw a little picture of what's happening. So I've got my planet Earth here. And of my planet Earth, I know that from the center to somewhere here, that's my r, my Earth's radius. Right. I also know that somewhere here, orbiting the planet is a satellite. So let's say the satellite is over there. Okay. I also know that there's two differences in terms of force. At my orbit, my force is force less than 4 times, right? And then at the surface over here, it's just force, right? We want to know what is the height. So this distance here in red, that distance r, we need to find r. So I know that if I take r and I minus big R, that's the radius. Let's do this and right here of Earth. Then I'm going to find my height. Okay. So this equation here is going to lead me to find that height. This I know. That I don't know. I need to go and find that. Right, so the first thing I need to do is I need to write out some equations that kind of make sense. So the first thing I want to look at is the gravitational force on the satellite and what the gravitational force is on Earth. So I've got F of my surface, which is G mass of Earth times mass of satellite all over r squared. And I've got force of my orbit, which is my satellite, and I've got G mass of the Earth times mass of the satellite over r squared. So I want you to notice the distances there are different. Right, the first thing I know is that at my surface, it's 4 times less. If it's 4 times less, what we're going to do for 4 times less is we're going to use a quarter. Right, so what we've got here is my force of my orbit is equal to a quarter of the force at the surface. Right, this just means 4 times less. Right, the next thing I need to do is put in my formula. So I'm going to use these two formulas and bring them into my equation. Remember what I said. What we know gets a value, right? Everything else is 1. Right, so let's have a look at how that's going to sort itself out. Force of my orbit, I've got G, mass of the Earth times mass of the satellite over r squared is equal to a quarter multiplied by G, mass of the Earth, mass of the satellite, all over r squared. Alright, there's my setup. Now all I've got to do is substitute in 1 everywhere. So here I've got 1 times 1 times 1. And I'm looking for r squared, so I'm going to leave that, is equal to a quarter, 1 times 1 times 1, all over r squared. So now I've got 1 over little r squared is equal to a quarter times 1 over r squared. I'm just going to solve mathematically. I'm going to solve my multiplication before I sort anything else out. Alright, so I've got 1 over r squared is equal to 1 over 4r squared. I'm then going to cross multiply. And I've got r squared is equal to 4r squared. Now remember, I'm looking to satisfy this equation. Okay, so I need r by itself, little r. So what I can do is to both sides, I can square root, and r is equal to 2r. Alright, now the equation that I want to satisfy is r minus r. Right, little r minus big R. I know now that little r is actually 2r minus r, and 2r minus r is actually just r. So I go back to my multiple choice. I need an answer that has an r in it, and then I'm left with number 1. And that is how you do a calculation like this. So you've got to take a little bit of time out and sort things out. You've got to use your maths. Oops. Right, question 4. A satellite experiences a force F when at the surface of the Earth. What will be the force on the satellite if it orbits at a height equal to the diameter of the Earth? Right, so all that's happening now is we just use basic ideas. I've got the planet Earth here. And from the center to above here, I've got a radius. I've also got from this end all the way to this end as my diameter. But now I've got something that's orbiting. Let's use a brighter color. Something that's orbiting. And that orbiting is from here, a diameter's worth there, it's orbiting something like that. So that's where the satellite is. Right? It's 1 diameter away. So what's actually happening here is that the diameter of the Earth is twice the radius. Right. So now I've got, remember, when we do forces, we work from here to here. So technically what I've got now is I've got this little portion there, and I've got that little portion there. This little portion is a radius, and that portion is a diameter, which is actually an r plus an r. So what we've done now is you have increased the distance of the satellite would be the radius of Earth, which is the little r, right? And so plus the diameter of Earth, right? Which is another r plus another r. So now you've increased it by a factor of 3. And if we increase by a factor of 3, and I go back to my equation, I can just say Fg is equal to G m1 m2 all over r squared. And what I've got here is 1 times 1 times 1 all over the r, which is 3 r's squared, and that's going to give me 1 over 9. 1 over 9. So by increasing by a factor of 3, your force is going to be reduced by 1 over 9. So if I go back here to my answers, the only answer I have there that's the correct answer is 1 over 9. So you've got to think. That's why I would strongly recommend that you draw an image, you look at what's happening, substitute your values into the formula, you should get the right answer. Alright, number 5. It says here the weight of a rock lying on the surface of the moon is W. So weight on moon equals just W. The radius of the moon is equal to r. So I can consider that a 1 value and a 1 value. There's nothing changing. On planet Alpha, the same rock has a weight of 8W. If the radius of planet Alpha is half of the moon, so the radius is a half. What is the mass of the moon? The mass of the moon is m, right? Is equal to m, which is also assigned a 1. What did they want the mass of planet Alpha? Right, so let's look at planet Alpha in terms of our formula. I know that Fg is actually equal to mg, which is then equal to g m1 m2 over r squared. Right. We're looking at alpha here, right? The mg they're giving us here is 8. The g is 1. The mass of the moon is 1. And we're looking for m2. And they're telling us that the radius is a half squared. Alright, so nice and simple. We've got 8 is equal to m2 all over a half squared, which is a quarter. So now I've got 8 over 1 times m2. So I'm going to cross multiply, and I've got 8 multiplied by a quarter, cross multiply, which is equal to 2, and m2. So the mass of planet Alpha is 2. So I go back to my answers and I look for an answer that gives me 2 as an answer, and the answer there is number 3. Alright, so that's the end of the worked examples. What you're going to have to do, and you'll have to send me a message when you're done so you can double check your answers. Let's have a look at what you're going to have to do. The first one is question 6. It says, consider the symbol of two physical quantities, G and G, used in physics. Name the physical quantities represented by G and G. B. Derive a formula for calculating G near the Earth's surface using Newton's law of universal gravitation. M and R represent the mass and radius of Earth, respectively. So that's 6A and 6B. Number 7. Two spheres of mass 800 grams and 500 grams are situated at their centers 200 centimeters apart. Calculate the gravitational force between them. Please remember, when you're doing this question, you've got to do some sort of conversion. Number 8. Two spheres of mass 2 kilograms and 3 kilograms respectively are situated so that the gravitational force between them is 2.5 times 10 to the power of negative 8 newtons. Calculate the distance between them. Right, please make sure you write down the base formula first before you do any sort of manipulation and move forward. Number 9. Two identical spheres are placed 10 centimeters apart. A force of 1.6675 times 10 to the power of negative 9 newtons exists between them. Find the masses of the spheres. Right, when you do a calculation like this, please don't forget that if the masses are identical, then you only need to solve for one mass, right? Next question, number 10. Halley's comet of approximate mass 1 times 10 to the power of 15 kilograms was 1.3 times 10 to the power of 8 kilometers from Earth. At its point of closest approach during its last sighting in 1986. Name the force, A. Name the force through which the Earth and the comet interact. B. Is the magnitude of the force experienced by the comet the same, greater than, or less than the force experienced by the Earth? Explain. And then the last question, question C over here. Does the acceleration of the comet increase, decrease, or remain the same as it moves closer to the Earth? So those are your 3 questions for question 10. I'll just do that. When you're done, send me a message. Ask me for questions 6 to 10, and you can see if you understand the section. But this is the end of the video. This is the last video. Please make sure that all of this is done before you're back at school when we get back for second term.